vector space. A vector space V plus and dot over R is a non-empty set V with two operations. Addition and scalar multiplication. Addition over V, output is V, and scalar multiplication R over V gives V, which satisfies the following conditions for all U, V and W in vector space V and for all scalars A and B in R. Additive closure. U plus V belongs to vector space. A dot U belongs to vector space. Additive commutative. U plus V is equal to V plus U. Additive associativity. U plus V plus W is equal to U plus V plus W. Existence of a zero vector. There is a special vector 0 belongs to vector space called the zero vector such that U plus 0 vector is equal to U. Additive inverse. For every U belongs to V, there is a vector U dash called the negative additive inverse of U such that U plus U inverse is equal to 0 vector. Unity 1 dot U is equal to U. Associativity of multiplication AB dot U is equal to A dot B dot U. Distributivity A plus B dot U is equal to A dot U plus B dot U, and A dot U plus V is equal to A dot U plus A dot B. Note: if just one of the vector space axiom fails to hold, then V not a vector space. Zero element, zero of vector of a vector space V is always unique. Zero vector is always unique. The real number 0 belongs to real number, and the zero vectors 0 V of a vector space V are commonly denoted by the symbol 0. One can always tell from the context whether 0 means the 0 scalar or the 0 vector. It is standard to suppress dot and only write AU instead of A dot U. A vector is an element of a vector space. Let's see the example. V is equal to Rn be the set of all n tuples x1, x2, xn of real numbers, that is V is equal to x1, x2 dot xn and x1 such that x1, x2, xn belongs to R. Consider the usual standard vector addition and scalar multiplication on V defined as follows: x1, x2, xn plus y1, y2, yn is equal to x1 plus y1, x2 plus y2, xn plus y1. ये हो गया एडिशन, and the scalar multiplication quality is c dot x1, x2, xn is equal to cx1, cx2 and cxn. These two properties should meet. The addition and multiplication on the left hand side are defined in Rn, whereas the addition and multiplication inside the bracket on the right hand side occur in R. Let's verify all the conditions for being a vector space to know whether V is a vector space or not with respect to the given addition and scalar multiplication. Let's see first additive closure. Clearly, if U is equal to x1, x2, xn belongs to vector space and V is equal to y1, y2, yn belongs to vector space, then u plus v is equal to x1 plus y1, x2 plus y2, and xn plus y1 is also in vector space, hence v is closed under addition. Multiplicative closure. Similarly, if c belongs to real number and u is equal to x1, x2, xn belongs to v vector space, then c dot u is equal to cx1, cx2, cxn is also in vector space, hence v is closed under scalar multiplication. Let's see the additive commutativity. Consider two arbitrary vectors u is equal to x1, x2, xn and v is equal to y1, y2, yn v, then u plus v is equal to x1 plus y1, x2 plus y2, xn plus y1. It is similar to y1 plus x1, y2 plus x2 and yn plus xn is equal to v plus u. U plus v is equal to v plus u. Therefore, u plus v is equal to v plus u for all uv belongs to v. Then it is additive commutativity also satisfied. Let's see the additive associativity. Consider three arbitrary vectors u, v and w, x1, x2, xn, y1, y2, y1 and z1, z2, zn. Then u plus v plus w. Let's see what it will be. x1 plus y1 plus w1, x2 plus y2 plus w2, xn plus yn plus wn, and u plus v plus w, what will be x1 plus y1 plus w1, x2 plus y2 plus w2, xn plus yn plus wn. Since each xi, yi and wi are real numbers and xi plus yi is plus wi is equal to xi plus yi plus wi for all i1 to n, we have u plus v plus w is equal to u plus v plus w for all uv belongs to v. So it is satisfy the additive associativity also. Let's check the fifth one, existence of zero vector. To get the zero vector, recall that the zero vector of a vector space V is a vector 0 such that u plus 0 is equal to u for all u belongs to V. Let u is equal to x1, x2, xn and 0 is equal to m1, m2, mn. Then we must have x1, x2, xn plus m1, m2, mn is equal to x1, x2, xn. Let's do the next step. x1 plus m1, x2 plus m2, like that xn plus mn is equal to x1, x2, xn. As a result, we obtain xi plus mi is equal to xi, so that mi is equal to 0 for all I is equal to 1 to n. Hence, 0 vector is equal to 0, 0, 0 is the zero vector of V with the property that u plus 0 vector is equal to u for all u belongs to V. So this property is also satisfied. Let's check the additive inverse. To find the additive inverse of an element u in V, we need to find an element u dash belongs to V such that u plus u dash is equal to 0 vector. Let u is equal to x1, x2, xn and u dash is equal to a1, a2, an in vector space V. Hence, we must have x1, x2, xn plus a1, a2, an is equal to 0 is equal to 0, 0, 0. So x1 plus a1, x2 plus a2, xn plus an is equal to 0, 0, 0. This gives x1 is plus xi plus ai is equal to 0. It means ai is equal to minus xi. Hence, minus x1 minus x2 minus xn is the additive inverse of u. Okay, this is also exist. Let's see the seventh property, unity. Take u is equal to x1, x2, xn belongs to vector space V and 1 belongs to real number, then 1 dot u is equal to x1, x2, xn for u all. It is satisfied. Associativity of multiplication. Let a b belongs to real number and u is equal to x1 x2 xn belongs to v. Then ab dot u is equal to what it will be? ab x1 ab x2 ab x1 xn. So it will be a dot bx1 a dot bx2 a dot bxn, like that. So let's take the common a, it will be bx1 bx2 bxn. Let's take the common b also, then it will be a dot b dot x1 x2 xn. So a dot b dot u. So it is associativity of multiplication. Distributivity. U is equal to x1 x2 xn and v is equal to y1 y2 y1 belongs to v and ab belongs to r. Then a plus b dot u is equal to a plus b x1 a plus b x2 a plus b xn. It will be ax1 plus bx1 ax2 plus bx2 axn plus bxn. ax1 ax2 axn take separate plus bx1 bx2 bxn take separate. Let's common a dot x1 x2 xn plus b dot bx1 x2 xn. So a dot u plus b dot u, it is proved. Distributivity over scalar addition. Then a dot u plus v is equal to a dot x1 plus y1 x2 plus y2 xn plus y1 ax1 plus ay1 ax2 plus ay2 axn plus ay1. So ax1 ax2 axn, let's take common, plus ay1 ay2 ay1, let's take common. So a common a dot u plus a dot v, you will get this one. All the axioms of vector space are satisfied, hence v is a vector space with respect to the given operation. Let's take an example. V is equal to M2 cross 3 matrix be the set of all 2 cross 3 matrices of real number. The usual standard vector addition and scalar multiplication on V are defined as follows. The matrix A11, A12, A13, A21, A22, A23, B11, B12, B13, B21, B22, B33 plus. If we'll do plus, then it will be A11 plus B11, A12 plus B12, A13 plus B13, A21, B21, A22, B22, A23, B33. Okay, this is the addition, usual addition, and the scalar multiplication will be CA11, CA12, CA13, CA21. This is the existence of zero vector. One can verify that the vector 0 is the zero vector of the vector space V with respect to the given operation. For any vector u belongs to V, the element minus u belongs to V is the additive inverse of u, and if we will add u with minus u, then we will get the zero vector. Just like in the previous example, we can check the other axioms to show that V is a vector space that with respect to the given operations. Okay, here are some other examples also. In every example, we will check the additive closure, multiplicative closure. If both are satisfied, then the vector should be in vector space. Okay, let's see this one. 1 1 and 2 3, it will be 1 1 and 2 3. It will be 3 minus 2, 2 3 and 1 1 will be 3 comma 2, 4 1 and 1 4, it will be 5 minus 3. We want to check whether V is a vector space or not with respect to the given operation. Okay, this is the let V is equal to R2 is equal to x1 x2 such that x1 x2 belongs to real number and the addition and scalar multiplication on v are defined as follows. Here not the usual addition and scalar multiplication, here it is defined. X1 x2 plus y1 y2 is equal to x1 plus y1 and x2 minus y2, and scalar multiplication c dot x1 x2 will be cx1 cx2. Let's see what it will be. Like if the vector is 1 1 and 2 3, then it will be 1 plus 2 and 1 minus 3. It will be 3 comma minus 2. 2 3 will be 3 comma 2, and 4 1 will be 5 plus minus 3. 4 1 and 1 4. We want to check whether V is a vector space or not with respect to the given operations: additive, closure, and multiplicative closure. Let's see, check. X1 x2 plus y1 y2 is equal to x1 plus y1 and x2 minus y2 belongs to V. Hence V is closed under addition. It is satisfied the additive closure, so it is closed under addition. Similarly, one can check that V is closed under scalar multiplication also, because there is no change. C dot x1 y1 will be cx1 and cy1, so no change. So additive commutativity, let x1 x2 and y1 y2, what it will be: x1 x2 plus y1 y2 is equal to x1 plus y1 and x2 minus y2. And if we will do y1 y2 plus x1 x2, it is a commutativity operation, and we will check it is it will be equal or not. So in the second step, what we will get: y1 plus x1, it is equal to x1 plus y1, and here it will we will get y2 minus x2, it is not equal to x2 minus y2. So this is different. It is clear that x1 x2 plus y1 y2 is equal to y1 plus y2 y1 y2 plus x1 x2 does not hold for all x1 x2 and y1 y2 belongs to V. Hence additive commutativity fails to hold. So V is not a vector space with respect to the given operations. Note, in fact, one can check that many of the axioms that a vector space must satisfy do not hold in this set with respect to the given operations. Let's see the next example. Consider the set V is equal to x1, x belongs to real number. The addition and scalar multiplication on V is defined, and what it is: x1 plus y1 is equal to x plus y and 1, and scalar will be c dot x1 is equal to cx plus cx and 1. So what it will be? If we will check the two vector 1 1 and 2 1, then it will the addition will be 1 plus 2 comma 1 and 3 comma 1, and 2 1 plus minus 2 1 if we will take, then it will be 0 comma 1, and scalar multiplication 4 dot 1 comma 1 will be 4 comma 1. We want to check whether V is a vector space or not with respect to the given operations. For that, we need to verify all the conditions one by one. Let's check the additive closure. If x1 y1 belongs to V, then x1 plus y1 will be x plus y comma 1 is also in V, hence V is closed under addition. And check multiplicative closure. Similarly, C belongs to R and x1 belongs to V, then C dot x1 will be cx1 is also in V, hence V is a closed under scalar multiplication also. And the third one is additive commutativity. U is equal to x1, V is equal to y1, then U plus V is equal to x plus y1 and v plus u will be y plus x1. Both are same, so it is additive commutativity property is also fulfilled. Let's check the additive associativity. U is equal to x1, p is equal to y1, and z is equal to w is equal to z1. B in v, then u plus v plus w will be x plus y plus z1, and in u plus v plus w will be x plus y plus z comma 1. It is also fulfilled. Existence of a zero vector. We are looking for an element zero vector belongs to v such that all u belongs to v. We have u plus 0 is equal to u. Let u is equal to x comma 1 and 0 vector is equal to m comma 1 in v. Hence we must have x1 plus m1 is equal to x1. So x plus m1, it will be x1. So x plus m is equal to x. So m will be 0. Hence the 0 vector is 0 comma 1. Additive inverse. To find the additive inverse of an element u in v, we need to find an element u prime belongs to v such that u plus u prime is equal to 0 vector. Okay. Let u is equal to x comma 1 and u prime is equal to a comma 1 in v. Hence we must have x1 and a1 is equal to 0 vector, yani 0 comma 1. Already we have calculated 0 vector is 0 comma 1. So x1 plus a1, x plus a comma 1 is equal to 0 comma 1. Using the addition defined on v, x plus a is equal to 0, so a is equal to minus x. Hence minus x comma 1 is the additive inverse of u, x comma 1. So additive inverse is also available. Let's see the unity. Take u is equal to x comma 1 belongs to v and 1 is a real number. Then if we multiply 1 dot u is equal to x comma 1 is equal to u for all u belongs to v, is also correct. Associativity of multiplication. AB belongs to R, u is equal to x comma 1. Then AB dot u is equal to ABX and 1. And A dot BX comma 1, A dot BX comma 1, and A dot B dot x comma 1, A dot B dot u. This is associativity of multiplication also fulfilled. Hence AB dot u is equal to A dot B dot u for all AB and u. Let's check the distributivity. Okay. U is equal to x1, B is equal to y1, and AB belongs to R. Then A plus B dot u is equal to A plus B x comma 1. AX plus BX comma 1. It will be AX comma 1 plus BX comma 1, because by our definition of is addition, so it will be A dot x comma 1 plus B dot x comma 1, so A dot u plus B dot u. It is also correct. A dot b plus b is equal to A dot x plus y comma 1, AX plus AY comma 1, AX comma 1 plus AY comma 1, A dot x plus 1 plus A dot y plus 1, A dot u plus A dot v is also okay. All the axioms of vector space are true for the given set V. Hence V is a vector space with respect to the given operation. Okay, here it is doing the example one more. V is equal to VR xy such that xy belongs to R. The addition and scalar multiplication of V are defined as follows: x1 y1 plus x2 y2 is equal to x1 plus x2 plus 1 and y1 plus y2, and c dot xy is equal to cx plus c minus 1 and cy. Okay, let's check. For example, 1 comma 1 plus 2 comma 1 will be 1 plus 2 plus 1 and 1 plus 1. Okay, it will be 4 comma 2, and 2 comma 1 and minus 2 3, what it will be, 2 minus 2 plus 1, 3 plus 1 is equal to 1 comma 4, and 4.11 will be 4 plus 4 minus 1, because it is a multiplication rule, cx plus c minus 1. So 4 plus 4 cx plus c, 4 plus 4 minus 4 comma 4 gy. Okay, it will be 7 comma 4. So existence of a zero vector, let's check for zero vector. xy plus mn is equal to xy होना चाहिए. So xy क्या होगा, x plus m plus 1 and y plus n, y plus n, and it will be xy. So x plus m plus 1 is equal to x, and hence m is equal to minus 1, and y plus n is equal to y, so n is equal to 0. M is equal to minus 1 comma 0 will be the zero vector for this, minus 1 comma 0. Minus 1 cancel, and 0 will be give y, so it is the zero vector. Let's check the additive inverse. To find the additive inverse of an element u in V, we need to find an element u prime such that u plus u prime is equal to zero vector. So let u is equal to xy and u prime is equal to ab in V. Hence we must have xy plus ab is equal to zero vector, and we have calculated it is a minus 1 comma 0, and it will be x plus a plus 1 and y plus b is equal to minus 1 comma 0. This gives x plus a plus 1 is equal to 0, and hence a is equal to minus x minus 1 and b is equal to minus y. Hence minus x minus 1 comma minus y is the additive inverse of u. Now you can check for unity also and associativity of multiplication. Okay, then distributivity, a plus b dot x1 y1 will be ax1 b plus bx1 plus a plus b minus 1 and ay1 plus by1. Okay, cy. Okay, so a plus b dot y1 equal to ay1 plus by1. So take ax1 plus a minus 1 together comma ay1 and plus bx1 plus b minus 1 comma by1. Where is 2 minus 1, ax1 plus a minus 1 bx1 or b minus 1. So a dot, it will be x1 y1 plus b dot x1 y1. 2 minus 1 कहाँ से आ गया भाई? So here you can it will be 2 minus 1 because for addition we will have the ax1 plus a minus 1 plus bx1 plus b minus 1 plus 1. This plus 1 is a definition of addition, so it will be cancelled and rest will be equal to this. Okay, and ay1 by1, it will be a dot x1 y1 and b dot x1 y1. So a dot u plus b dot u. Distributivity is also fulfilled here. A dot u plus v is equal to a dot x1 plus x2 plus 1 y1 plus y2 ax1 plus ax2 plus a minus 1 ay1 ay2. Scalar multiplication includes minus 1, so it is a plus a. Scalar multiplication definition, let's check once. It is c dot xy is equal to cx plus c minus 1. Okay, cx plus c minus 1. So from there we will get the cx plus c. This is x, cx यहाँ तक plus c यानी a minus 1 ay1 ay2. So take ax1 plus a minus 1 comma ay1 plus ax2 plus a minus 1 ay2, because when we will add the, you get plus 1 extra and it will cancel this minus 1. So first one will become a x1 y1 plus a dot x2 y2. So a dot u plus a dot v. Checking other axioms are easy, hence v is a vector space with respect to the given operations. Okay. Properties of vector spaces. Theorem. Cancellation law of vector addition. Let v be a vector space and v1 v2 and v3 are in vector space v. So if v1 plus v3 is equal to v2 plus v3, then v1 is equal to v2. Proof. Let's prove it. Since v is a vector space, the element v3 belongs to v has an additive inverse v prime v3 prime, thus that v3 plus v3 prime is equal to 0 vector. Therefore v1 plus v3 is equal to v2 plus v3 by assumption. So let's v1 plus v3 add v3 prime both sides by adding v3 prime to both sides, and conclude it with v1 plus v3 plus v3 prime and v2 plus v3 prime by additive associativity. So it will be v1 plus 0 vector is equal to v2 plus 0 vector. So by this it is proved that v1 is equal to v2 because 0 is the 0 vector. Similarly, one can show that a vector space v, if v3 plus v1 is equal to v3 plus v2, then v1 plus v2. Corollary. Zero vector of a vector space v is unique. That is, if there are vector 0 and 0 prime satisfy the property of 0 vector, then 0 vector and 0 prime vector both are same. For each vector u belongs to v, the additive inverse u prime is of u is also unique. Let's prove it. Suppose 0 vector and 0 prime are two additive identities of v, since 0 vector is an additive identity. So 0 prime plus 0 is equal to 0 prime. Since 0 prime is also an additive identity, so 0 prime plus 0 prime is equal to 0 prime. Therefore from equation 3.2 and 3.3, 0 prime plus 0 is equal to 0 prime plus 0 prime. And cancellation law say 0 prime vector from both sides will be cancelled, and it will be proved that 0 vector is equal to 0 prime vector. Suppose u prime and W are two additive inverse of U, then U plus U prime is equal to 0 is equal to U plus W. By cancellation properties, we will cancel this U both side, then hence it will be proved that U prime is equal to W, and his U prime is also a unique vector. Okay, next check the corollary 3.3.3. For all U belongs to V, we have zero vector such that the 0 dot U is equal to 0 vector, where 0 is the 0 scalar and 0 vector is the 0 vector. This is 0 scalar, it is a 0 vector. If we multiply 0 scalar to the any vector U, we will get the 0 vector. For all C belongs to real number, we have C dot 0 vector is equal to 0 vector, and for each C belongs to R and for each U belongs to V, we have minus C dot U is equal to minus C dot U is equal to C dot minus U. Let's prove it. Since 0 is equal to 0 plus 0, we obtain 0 plus U is equal to 0 plus 0 dot U, because 0 plus 0 is also 0. Since scalar multiplication is distributive over addition, distributive property, so 0 plus 0 dot U is equal to 0 dot U plus 0 dot U. From the last two equalities, we get 0 dot U plus 0 dot U is equal to 0 dot U. Last two equalities. So 0 dot U plus 0 dot U is equal to 0 dot U plus 0 vector, because 0 dot U is equal to 0 vector. So 0 dot U is equal to 0 vector, cancellation law of vector addition. Dot U is equal to 0 vector. Proof of this is similar to proof I. Since C is equal to C plus minus C is equal to 0, we obtain 0 vector is equal to 0 dot U is equal to C plus minus C dot U. It is C dot U plus minus C dot U, and C dot U is the additive inverse of minus C dot U, that is minus C dot U is equal to minus C dot U. Similarly, we can show that C dot minus U is equal to minus C dot U. Okay, let's take the next interesting topic, subspaces of vector space. What is subspaces of a vector space? Definition: a non-empty subset W of a vector space V is called a subspace of V if W is a vector space under the operations addition and scalar multiplication defined in V. Non-empty subset W of a vector space V is called a subspace of V if W is a vector space under the operations addition and scalar multiplication defined in V. To show that a non-empty set W is a vector subspace, one doesn't need to check all the vector space axioms. It is enough to check two axioms of a vector space. What is this? If W is a non-empty subset of a vector space V, then W is a subspace of V if and only if the following conditions hold. These two. Number one, if W1 and W2 are in W, then W1 plus W2 belongs to W. W1 and W2, the addition, it is a closed under addition, because W1 and W2 also belongs to W, and for all C belongs to R, and for all W1 belongs to W, C dot W1 belongs to W. A subspace W of a vector space V is called a proper subspace if W is a subset of V. Every vector space V over R has two trivial subspaces. Every vector space V over R has two trivial subspaces. V itself is a subspace of V, the subset consisting of the zero vector of V is also a subspace of V. The subset consisting of the zero vector of V is also a subspace of V. So that V and zero vector are subspaces of vector space V. Example: consider the vector space V is equal to R2 is equal to xy such that xy belongs to real number with respect to the usual addition and scalar multiplication. X1 y1 plus x2 y2 is equal to x1 plus x2 and y1 plus y2. C dot x1 y1 is equal to cx1 cy1. We want to check whether w is equal to xy such that x plus y is equal to 0. Subset of R2 is a vector subspace of V is equal to R2 or not. Note that W is a non-empty and a proper subset of V because 1 comma 1 belongs to V but 1 comma 1 not belongs to W. By theorem, it is enough to show that W is closed under addition and scalar multiplication. Let W1 is equal to x1 y1 and w2 is equal to x2 y2 belongs to W. Then by the definition of W we have x1 plus y1 is equal to 0 and x2 plus y2 is equal to 0. To show that x1 y1 plus x2 y2 is equal to x1 plus x2 and y1 plus y2 is belongs to W, it is enough to show that x1 plus x2 plus y1 plus y2 is equal to 0, which is obvious. Next we want to show that C dot x1. Okay, thank you.